Today we'll be looking at metamorphic rocks. In this presentation, our objective is to compare and contrast the types of metamorphism, classify each metamorphic rock, and differentiate between diagenesis and metamorphism. If we recall the rock cycle, we have already discussed igneous rocks that directly come from melting, wherein you have extrusive rocks as a result of magma crystallizing on the surface, and intrusive rocks characteristic of those that are crystallized underneath the surface of the earth. We've also discussed sedimentary rocks, which come from pre-existing rocks, or precipitate from ions, or come from a biologic process. After which, during burial, higher pressures transform our rock into metamorphic rocks. Not just that, we can also have metamorphic rocks as a result of high pressures from meteorite impacts or high temperatures, not enough for melting, but enough to change the rock in its solid state. What is metamorphism? Metamorphism is a change undergone by an existing rock or pre-existing rock, as I said, in the solid state and transforms into another rock. Why do these rocks change? It is because of the agents of metamorphism. These include heat, pressure, and chemically active fluids. What do these agents do to change these pre-existing rocks? As an agent of metamorphism, heat is sourced from the geothermal gradient, which is a temperature increase with depth, roughly 20 to 30 degrees Celsius per kilometer in the crust. Also, large intrusive bodies can also emit heat in order to change the surrounding rock. So, these provide energy to drive chemical reactions, which in turn recrystallizes your minerals. In terms of pressure, we have different types of stresses. Confining and differential stress, when applied to the rock, changes its appearance and as well as sometimes leading to recrystallization. Take note that the recrystallization tends to form minerals in compact forms. But what about chemically active fluids? Chemically active fluids come from water that comes from pore spaces, dehydration of minerals such as amphibole or mica, and also water from magmatic bodies, sometimes called juvenile. Because of the different types of agents of metamorphism, the types of metamorphism also differ. The first of these is contact metamorphism. It occurs when magma invades pre-existing rock and alters these rocks in a zone of alteration called an aureole, which forms around the emplaced magma. This takes place at shallow depths, roughly 0 to 6 kilometers, and at low pressures. What would it produce? Foliated or non-foliated rocks. These terms are associated with textures, foliated being an alignment or parallel alignment of minerals, and non-foliated with no alignment at all. Given that there's low pressures, usually non-foliated rocks are a result of this type of metamorphic process. Some examples would be marble, which comes from the contact metamorphism of limestone, and quartzite, which comes from the contact metamorphism of quartz sandstone. Here we can see an example of a contact aureole that is seen grading from a higher grade metamorphism near the magma chamber, and as you get away from the magma chamber, you have lower grades of metamorphism. As mentioned, quartz sandstone, which is a protolith or a pre-existing rock, turns into quartzite when subjected to heat and low pressures. Limestones transform into marbles, and shales transform into what we call hornfels, which are very durable types of contact fine-grained metamorphic rocks. Another type of metamorphism is called regional metamorphism. This occurs in high-pressure areas at considerable depths, roughly from 5 to 20 kilometers, and sometimes even greater than 30 kilometers in depth. This is associated in subduction zones as well as in the process of mountain building. Recall that foliated rocks have parallel alignments, while non-foliated rocks do not have these types of alignments. Because of the pressure conditions, foliated rocks are the result of regional metamorphism. Okay. We'll discuss further the types of metamorphic rocks. Foliated in this case, where you can see slates, phyllites, schists, and gneisses. We'll talk more about this in the succeeding slides. Another type of metamorphism is hydrothermal alteration. This occurs at high temperatures and moderate pressures, but by hot iron-rich or hydrothermal fluids that circulate through fissures and cracks. This usually occurs in mid-oceanic ridges where black smokers are seen in these areas. These are associated with very rich ore deposits, as mentioned in previous lectures. Shock metamorphism occurs when an extraterrestrial body, such as a meteorite or comet, hits the Earth with very high pressures, and the generated rocks are usually polymorphs of low temperature minerals in high temperature form, such as with quartz, polymorph of caesite and stishovite. Here you can see examples of craters that have formed due to high impacts of these meteorites or comets. Here we can see an example of caesite and stishovite, which again are high pressure forms of quartz. Now let us classify metamorphic rocks. How do we classify metamorphic rocks? We usually do this based on texture, which is the size, shape, and relationship of constituent minerals, and the protolith, which I have mentioned is the original rock that was transformed by metamorphism, or the pre-existing rock that was transformed. Take note that in low-grade metamorphic rocks, original textures may still be preserved and might allow the determination of the likely protolith. Interestingly, sometimes if you walk from the higher pressure areas or higher contact metamorphism areas and walking towards the lower grades of metamorphism, you may or may not find the protolith of your rock. Also, the classification of metamorphic rocks is also determined by the mineralogy or the mineral assemblage that is present in your rock. As I've mentioned, the protolith again is the pre-existing rock. And interestingly, the parent rock, for example, shale, may even turn into slate and schist and gneiss, depending on the temperature and pressure conditions of your area. As I've mentioned, sandstones can turn into quartzites, limestones into marbles, and in this case, We've mentioned in the sedimentary rocks lectures that bituminous coal in millions of years may turn into anthracite coal, which is a metamorphic rock. We'll discuss what slate, phyllite, schist, and gneiss are in the succeeding slides. As I've mentioned, foliated and non-foliated rocks. These are types of textures of metamorphic rocks. Foliated exhibits parallel alignment of minerals and/or, in this case of gneiss, compositional and mineralogical layering in the rock. Non-foliated rocks, again, have no preferred mineral orientations. There is only a transformation of one mineral to another. Foliation occurs where rounded grains can become flattened and minerals can have a preferred orientation. Usually, you have confining pressure differential stress, which allows these minerals to flatten and align themselves towards the plane of least resistance. Examples of foliated rocks are slate, phyllite, schist, and gneiss. Slate is a low-grade foliated rock, which consists of a slaty cleavage, which allows the rock to be broken in planes of weakness. Phyllite, on the other hand, is an intermediate-grade foliated rock with a phylitic texture sheen which results from the growth of pearly micaceous minerals, which are still too small to be seen. As the grains become coarser in texture, an intermediate to high-grade rock called schist results, which has parallel to subparallel foliation of medium to coarse grained platy minerals. As you increase the pressure and temperature conditions, a high-grade metamorphic rock called gneiss with gneissic texture results. How does gneissic texture form? If I have a granite, for example, which is subjected to differential stress, there is a parallel alignment of minerals as well as the separation of mineralogical compositions in layers, in this case of felsic minerals and mafic minerals. And this is again called gneissic layering. What about migmatite? Migmatite is a special type of rock or metamorphic rock that has had some sort of partial melting, and you can see that there are two intermingled but distinguishable components, typically a granitic rock with a metamorphic host rock. Metamorphic grades. We use metamorphic grades to describe the relative temperature and pressure conditions under which your metamorphic rock forms. As I've mentioned, from slate all the way to gneiss, there are a range of grades. Slate having low-grade metamorphism, phyllite from low-grade to intermediate, schist from intermediate to high-grade, and gneiss having high grade of metamorphism. In line with this, some of your metamorphic minerals form, which also indicate these types of temperature and pressure conditions. If a chlorite is found on a phyllite, for example, we can call it a low-grade type of metamorphic rock. But as you get higher into types of metamorphic minerals such as garnet and staurolite or sillimanite, then you can surmise that these types of temperature and pressure conditions are much higher. So some examples of metamorphic rocks found around the Philippines, which occur in collision zones such as in Romblon Island. In this case, you can see some of the folding that has occurred in this type of rock. These are dynamically formed metamorphic rocks, and so on and so forth. These folds, when named, are sometimes called granulations, which occur in your metamorphic rocks. A myriad of resources come from your metamorphic rocks. An example is marble, which we use for statues, such as the Michelangelo statue, from which it was carved. Slate, because you can cut slate along its weak planes. They use this for roofing, for billiard tables and blackboards. Talc, as we know, can be ground into a fine powder. Graphite, which is commonly known as lead in pencils, is also used as a lubricant. Garnet and corundum, for their high hardness, are used as gemstones and abrasives. Kyanite, andalusite, and sillimanite, which are the polymorphs that we've mentioned in our mineral lecture, are used as raw materials for our ceramics industry. As mentioned, rich iron ore deposits, called sulfide deposits, occur in hydrothermally altered areas. Also, iron and tin oxide deposits. Tungsten is also gathered from metamorphic sources, and of course, sometimes gold or precious metal deposits. So here are pictures of marbles used as ornaments. This is a sulfide hosted ore deposit, slate as roofing, and garnets, which are polished and cut into gemstones. Metamorphic environments are associated with plate tectonics, where high temperature and low pressure zones result in contact metamorphism, high pressure and high temperature zones for higher grades of metamorphism, and in trenches where we have high pressure and low temperature areas, which can result in your regional metamorphic rocks. We also have something called metamorphic facies, which are mineral assemblages that are useful in indicating temperature and pressure conditions that formed your rock. So here is an example of the plotted pressures on the y-axis and temperatures on the x-axis, and the resulting facies that occur along these types of pressure and temperature conditions. For example, zeolite facies occurs in low temperature and low pressure areas, while eclogite facies are in moderate temperatures but higher pressure areas, and so on and so forth. Some examples of the rocks or the types of rocks that occur in these zones are green schists, which are named according to the mineral assemblage containing chlorite, actinolite, and albite. Blue schist or glaucophane schist for its naturally blue color due to the presence of glaucophane and other types of blue minerals. And of course, eclogites, which kind of look like Christmas, which have your reddish garnets and your sodium-rich green omphocytes. As mentioned, kyanite, sillimanite, and andalusite are found in your metamorphic rocks. These are anhydrous aluminum silicate minerals with the same chemical formula but different structures. As mentioned before, these are polymorphs. And looking or finding these particular minerals tells us a lot about the temperature and pressure conditions during its formation. Again, these are useful in the ceramics industry. Metamorphic rocks occur in collision zones along the Philippines. Recall that you have subduction zones in these areas, rather the East Luzon Trough, the Philippine Trench, and the collision between Eurasia and the Philippines along Mindoro and Palawan. as well as the subduction zone here in the Sulu Trench, and so on and so forth. That is all. I hope this particular lecture helps you visualize and understand the different processes and the resulting rocks from metamorphism.